So in this lecture, we will discuss a new data structure, stack. So what is a stack? Okay, uh, there is a data structure stack, and we will also discuss another data structure queue after the discussion of stack is completed. So both stack and queue have some similar property. Okay, there are certain frequent situations in computer science when one wants to restrict insertion and deletions so that they can take place only at the beginning or at the end. Insertion and deletion cannot be performed in the middle in those situations, right? So in those situations, two data structure stack and queues are suitable. In both stack and queue, insertion and deletions can be performed only either in the beginning or at the end, right? So we will discuss these two data structures. First, we will discuss stack, and after that, we will discuss queue. Okay, so what is a stack? A stack is a list of elements in which an element may be inserted or deleted only at one end, called the top of the stack, right? So in the stack, insertion and deletion can be performed only at one end, and that end is called top of the stack. Okay, so in the insertion operation in the stack is called the push operation. Okay, push means insert an element into the stack, and delete operation is called the pop operation, right? So pop means delete an element from the stack. Okay, so for example, say this is your stack. Okay, and uh, the literal meaning of the stack is that you start putting things over and over again. Okay, that is, you put, for example, here you can see that some user has put this green, sorry, this brown disk. Okay, assume that these are disk. So the first, this brown disk is put on the table, right? Then over that the green disk is put, and then this one, and this one, and this one, right? So this is the stack, and now the user tries to put this blue disk. Okay, so the user is inserting disk into the stack. Okay, so insert operation is called push operation. So push this blue disk into the stack. Okay, so after this blue disk has been pushed onto the stack structure will be like this. Now at the top of the stack, this is the top of the stack, you have the blue disk. If you want to remove this blue disk, you need to pop the top element. Okay, pop the top element, and the top, at the top of the stack you have the blue disk, so it will be removed. If you perform the pop operation again, the current top, which is now this yellow disk, will be removed. Okay, so push operation insert an element. The push operation requires one argument, one parameter, the value of the element which is being pushed, which is being inserted. Okay, so here in this case, push the blue disk. Okay, so push operation and argument is the blue one, right? And pop operation does not require any argument because it always removes that element which is at the top of the stack, right? So push requires one argument, the value of the element which is to be inserted, which is to be pushed onto the stack, and pop does not require any argument. Okay, so stack stores a set of elements in a particular order, and what is that order? That order is last in, first out, LIFO. Okay, last in, first out. What does it mean? The element which is inserted in the last will be removed first. Okay, here in this particular example, you have seen that this blue disk was inserted last. Okay, and is removed first. You insert blue disk, pushed the blue disk into the stack, right? And if you want to delete an element, you have only one option. The top of the stack can be removed, and at the top you have the blue disk which is just inserted. Okay, so this is LIFO, last in first out. The blue disk was inserted in the last and will be removed first, last in first out. So stack is a structure which is also called LIFO. Okay, sometimes stacks are also called push down list. Okay, because the elements are inserted uh, as you are pushing the elements down into the stack. So they are also called push down list. Right. So stacks are LIFO. The element which was inserted last will be removed first. Example. So initially your stack is empty. There is no element. Okay. Then you push an element A. Right. So this is the position of the stack. You have one element A in the stack, and the top is a pointer which always point to the location where the last inserted item is stored. Okay, so here the last inserted item is A, which is on the top of the stack. So this top pointer or top variable stores the address of the last inserted element A. Right. Next, push B. Okay, so push B will insert element B over A. Right, now top point to element B, that is top, it shows the address of element B. Then push C. Okay, C is inserted and top is modified. Then push D. D is inserted into the stack and top is modified. Right, now you try to remove some elements. Pop, there is no need to provide the argument to the pop operation because pop always remove elements from the top. So at the top you have element D. So D will be removed and top will be modified. Now top will point to the next element from the top, that is C. So now top points to C. Okay, this is the situation. Now remove another element, the pop operation. The C will be removed and top will point to the next element from the top, which is B. Remove another element. Okay, pop. So now B will be removed and you will have only A. If you perform another pop operation, the last element in the stack A will also be removed. So only two operations are possible, pop and push. Now applications of the stack. Where stacks are used? Stacks are used for postponed decisions. Postponed decision means where some decisions need to be postponed until some other conditions are met. Okay, so to indicate the order of processing of data when certain steps of processing must be postponed until some conditions are fulfilled. For example, there are say three projects: project A, project B, and project C. Okay, and a team starts working on project A. Okay, after some time they feel that project A requires some functionalities of project B, and project A cannot be completed until those functionalities of project B are incorporated in the project A. So what the team will do, project A will be stopped, they will stop working on A and will start working on B, because A cannot be completed until B is complete, right? So now A is halted and B is started. After some time, they realize that B cannot be completed until C is complete because it requires the functionalities of the project C. So again, B is halted and C is started. Okay, the team works on C and completes its working. completes is and complete project C, right? So after that, now project B can be completed. So they start working on B and finishes it. Okay. Now since B is finished, now project A can be started again. Started again from the point where it was halted, and then the remaining portion of A is finished. Right. So in this situation, so stack can be used to remember the order of execution of the project, right? So for example, when A is started, you push project A into the stack. This is the position A. Now A is halted and B is started. So you pushed B into the stack, this one. Now B is halted and C is started, position C. Now C is inserted, pushed in onto the stack. Now next step, C is finished because C does not depend on any other project. So C is finished. Okay. Now C is finished, so we will remove project C from the stack. So C is removed. So stack position will be like this. C has been removed. So now team is working on project B. Okay. Project B is finished. So B will also be removed. So this is the next position of the stack. Okay. Now team works on project A and finishes it. Then A will also be removed and you will have an empty stack in that. Okay, so stack can be used to store the order of processing. Okay, where postponed decisions are required. When one event must wait, one action or event must wait for some other action or event to complete it. Right. Some practical examples: page visited history in a web browser. To store the history of a web browser, stacks are used. Okay, why? Because when you view the page visited history, which address of the page, which page address is shown first? The page which was visited last. Okay, so the page which was visited by you in the last is shown first. So LIFO, last in, first out. Okay, so the data structure used to store the page visited history in a web browser is stack. Okay, another example, undo sequence in a text editor. Okay, when you press the undo button, which of action is undone first? The action which was performed in the last. Okay, you press the undo button again, then the second last action will be deleted, will be undone, right? So undone sequence is also stored in a stack. Okay, saving local variables when one function calls another. Okay, so for example, say there is a function f1 and f1 call function f2 and f2 call function f3, right? So function f1 is calling f2. So f1 cannot complete its execution until f2 is finished because f1 has called f2, and f2 is calling f3. So likewise, f2 cannot finish its execution until f3 is free. Okay, so you can store these in the stack. How? So first f1 is executed, so f1 is pushed into the stack. Then f1 call f2, f2 is inserted into the stack. Then f2 call f3, f3 is inserted into the stack. Now f3 is finishes execution, so f3 is popped out. Then f2 finishes execution, f2 is popped out. Then f1 finishes execution, so f1 is popped out. Okay, so local variables, in fact, not only the local variables, that all the data related to the function are stored in the stack, and that stack is basically maintained by the operating system. So there is a function called mechanism. Whenever a function is called by some other function, okay, the activation record instance ARI is pushed into the stack. Okay, and that stack is maintained by the operating system. And that ARI of the function contains all the information related to that function. Okay, that includes the function prototype, that includes the all the local variables, that includes all the parameters. Okay, that includes the return address of the function. Okay, and other information, right? So ARI are pushed. So there are some applications. Okay, you can identify a lot of other applications. In fact, we will discuss some applications of the stack uh, in the next few lectures. For example, we will be discussing the various notations of writing uh, expressions, the infix and postfix and prefix notation of writing expressions, and how you can convert one notation into another notation. We will also discuss quicksort, which uses the stack. Okay, quicksort can be implemented using an explicit stack, and it can be implemented recursively where the use of the stack is implicit. Okay, so we will discuss both of those variations. We will also discuss a tower of Hanoi problem, which uses a stack. Okay, so several problems. Although stack is a very simple data structure, but it is used very heavily in computer science. Okay, stack ADT. Okay, so we have discussed what is an ADT and how it differs from the data structure. In the data structure, we also talk about the representation and the implementation. But in the ADT are independent of all these talk. We don't talk about the representation. We don't talk about the implementation detail. We just state the what is data. Okay, some a mathematical model is used. Okay, and the mathematical model can be as simple as using some natural language statement, right? And we also state the operations which can be performed on those data. Okay, so what are the data? What is the data in the stack? Okay, so what are the objects? Stack is a finite sequence of nodes. Okay, finite sequence. Sequence is an order list. And how the order of element in the stack is defined? The order is LIFO order, right? So, and what operations can be performed? You can create a new stack, right? You can push a new element at the top of the stack. Elements are always inserted at the top of the stack. Okay, top operation return top element. Okay, top operation returns the value stored at the top position of the stack, right? And it is different from the pop operation. Pop operation remove the element stored at the top of the stack and return it, right? Top operation does not remove the element from the top of the stack. It simply returns its value, right? So pop operation remove the element and returns it. Top operation simply returns the value stored at the top. It does not remove. Okay, a boolean operation which returns a boolean value is empty. Okay, it tests for the emptiness whether the stack is empty, whether the stack has some element or not. So these are the operations which can be performed on the stack. Okay, there is a situation when the stack might be underflow. Okay, so if the stack is empty and you try to perform either pop operation or the top operation, since the stack is empty, there is no element present in the stack, so both of these two operations, pop and top, will throw an exception. We call that exception underflow. Okay, how the stacks can be represented? Can be represented in two different ways, using linear arrays and using one-way linked list. So first, using the array representation. Okay, so in the array representation, an array of fixed length, obviously array always has a fixed length. So arrays are used. Size of array is fixed, so the size of the stack is also defined by the size of array, which is being used to represent the stack. We define two variables, top and max stack. The top variable always points to the top of the stack, always points to the element which is at the top of the stack currently, and max stack is the size of the array which is being used to represent uh, that stack. Okay, so for example, here you can see we are using an array and the size of this array is 8, and currently there are 3 elements. At the top we have ZZZ and its location is 3. So top variable is stored the address of the top element. Top element is ZZZ and its location is 3. So top will store 3, right? And max stack is the size of array. Size of array is 8. So max stack will store 8. Okay, so this is 8 basically, not 3. Right, so max stack is the size of the array which is being used to store the stack, and top always points to the top element of the stack. Now the algorithm for the push operation. So name of the array which is being used to represent the stack is stack variable top pointing to the top element. Max stack is the size of the array stack. Remember now the stack is the name of the array, and we are going to insert or push the new element whose value is item, right? So you need to check for the overflow condition because the size of the array is fixed. So if the array stack is full, you cannot insert new element into the stack. Okay, so you must check. And what is the overflow condition? If top is equal to max stack. Okay, so it means that the array is full, the stack is full, right? The top element is at the maximum position of the stack. Okay, then print overflow and return. You cannot insert a new element because the stack array is full. Otherwise, what will you do? The new element is always stored at the top of the stack. So currently the value of top indicates the top location, top full location of the stack, right? So the new element will be inserted above it. So you will increment the value of top. Top is equal to top plus 1. Okay. Then item will be stored at that top. Okay. So the two statements. First you increment top, and then item will be stored at location exact top. Then algorithm returns. So this is the push operation. Likewise, you can write pop operation. Okay. Stack operation. Stack data structure, top variable, and item variable, right? So here you need to check for the underflow condition. Okay, if there is an element or not. If top is equal to 0, 0 means null. So if top is equal to null, it means there is no element in the stack and you cannot delete an element. So you print underflow and return. Okay, otherwise you collect the top element, stack top, in the variable item. Okay, and then you decrement the top variable because now the top will point to the next top element, the element which is next to the top. So top is decreased by 1, and then the algorithm returns. So these two operations are very simple. Okay, minimizing overflow. So in the array representation, you see that the size of the state is size of the stack is defined by the size of the array. The size of the array is 8, the size of the stack is 8. Okay, so if the memory allocated to the stack is small, okay, and you keep inserting new elements into the stack, you will soon reach to the overflow condition. Okay, and since during the execution of the program elements will be removed, then inserted again, then some elements will be removed, then some new elements will be inserted. Okay, so during the entire course of execution, several times you can reach to overflow condition. Okay, so there is a time space trade-off between the number of overflow conditions and the stack space. So if the allocated space to the stack is small, you will find several times the overflow condition. You'll find the overflow condition several times. But if the stack space is very large, then you will not find any overflow condition because the stack space is very large. Okay. So the issue is that if you allocate more space, then probably some space will be wasted because at some time the number of element in a stack is very small and you have allocated more space, large space. So a lot of space of memory would be wasted. If you allocate less memory to the stack, then you will find the overflow condition several times. Number of overflow will increase. Right, so there is a trade-off between the number of overflow conditions you find during the execution of the program and the stack space. Right, so to better use both the time and the space resources, several techniques can be proposed, several methods are proposed to handle those situations in a better way. One possible solution is that is you use the same array to store two stacks. One stack is stored from left to right, and the second stack is used to store from the right to left. Okay, so here stack A is being stored from left to right, and stack B is being used to store the elements from right to left. Right. So in this way, you can see that if both stack A and B are large, if the number of elements in both stacks A and B are very large, in that case, you will get an overflow condition. Okay, if any one of the stack A or B is small, then probably you will not get any overflow condition. Okay, so this this method manages the stack space and the overflow condition in a better way. Okay, linked list representation. In the linked list representation, we use a single linked list, singly linked list or one-way linked list. Right. So now, and the linked list, we restrict that the elements can be inserted only in the beginning and deleted only in the beginning. Other operations like insertion in the end, in the middle of uh, linked list are not allowed. Similarly, deletion at the end and in the middle are not allowed. The insertion and deletion the linked list can be performed only in the beginning. Okay, so here you can see this is some state of the linked list. There are three elements x, y, and z. Okay, so this is the top. Now the start pointer of the linked list is named as top. Okay, so top points to the first element, which is the top of the stack. Okay, and at the bottom of the stack, that is the last element of the linked list is here is z, and that last element in the link part we have stored null. Okay, right. So this is the stack linked list representation of the stack. Now how the push and pop operations are performed. For example, say this is the current position of the stack stored using a linked list. Okay, you pushed a new element w. So w will be pushed on top of the stack, and here we are using linked list. Okay, so it means this w will be inserted as the first element of the link. So here you can see that this w is inserted as the first element of the link. Okay, and you know how a new element is inserted at the beginning of the link. We have already discussed this. Similarly, the pop operation, when the pop operation is performed on a stack which is maintained using a linked list. Okay, so the first element of that linked list is removed. Okay, so this element will be removed when pop operation is performed. So now the top will point to the next element, second element of the linked list. Okay, so you can write algorithm for these. Okay, so assume that we have a linked list with info part and the link part. Okay, we have the top pointer. Okay, instead of start, we have the top pointer which points to the first node of the linked list. Okay, and that first node is also the top element of the stack. And we have the avail list which contains the list of all nodes which are free and the value item which is to be inserted into the stack. Right, so first check for the overflow. Okay, because the new node which is to be inserted, the space for the new node comes from the avail list. So there is no element in the avail list, it means overflow, right? So, and if there is a node in the avail list, then remove that first node from the avail list. These are the statement: new is equal to avail and avail is equal to link avail. We have already discussed these statements. Okay, then you store the item in the information part of that new node. Okay, now this new node is to be inserted as the first element of the linked list, right? So top is the first pointer, so in the link part of that new node you will store top, and now this top pointer will point to the new node, right? And then next. So it's very simple. It's as simple. In fact, this is similar to the insertion at the beginning in a linked list. Similarly, pop operations can be specified. Okay, linked list with info, link part, top pointer, avail list, and the value of the node which is to be deleted is collected in the variable item. Okay, check for the underflow condition. Okay, if top points to null, means no node in the linked list. So it means you cannot delete an element, print underflow, and then exit. If there is an element in the stack, then collect that item, collect that value in the item. So information part of the node pointed at by the top is collected in the item, right? And then we use a temporary variable temp to store the value of top. Okay, and then top is set to the link top. Link top is that is of the next node, second node. Okay, and which is basically the element uh, which is the element on the stack at the second last position. Okay, just after the top location. So top will be set to link top. The top will be top points to the next location, right? And we have collected before this statement, we have stored the value of top in the temp, right? So now this node will be stored in the avail list as the first node. So link temp is equal to avail, right? And avail is equal to temp. That new node is added to the avail list as the first element. Exit. So this is the pop operation. Okay, some example schematic diagram of performing operations when the stack is represented as linked list. So this is the original linked list having three elements. Top points to the first element of this linked list. Push a new element B. So B will be inserted as the first element. Okay, top is adjusted. Pop. Pop remove the first element of the linked list. So B is removed. Now top is pointing again to X. Pop again. So X will be removed and top now points to Y, and then you push M. Okay, so a new node containing M will be inserted as the first element in this linked list. Okay, top pointing to M now. So this is you can represent and implement operations using linked list for the stack. Right.